Well, thank you all for coming, for your interest in this topic also, and coming to the CCSS. It's a real pleasure to introduce Prof. Restrepo, who is section head mathematics and computation at Oak Ridge National Lab in Tennessee, near Knoxville. And we just, spent a week at SCIEM, computational science and engineering, and it was nice to escape.
Yes, it was. Yes.
It was an impressive conference in Amsterdam. So Juan has an interesting, CV. He started out as a professional musician. Did actually a BSc in music in New York University. That's quite a while back, 1983, right? If I see it, so that's why I know that. But then decided that science was more fun, than music. Also, probably having more constant living.
That was true. Well, in those early 80s, it was bad hair, bad music. It was bad everything.
Exactly. So he got a PhD in physics in 1992. And then had a long-time position at Oregon State University.
University of Arizona.
First University of Arizona, I see that. Then in Oregon, right?
Yeah.
And now in Oak Ridge National Lab. He's a SCIEM fellow. This is very 2018. Also APS fellow, so the American Physical Society. And so he's distinguished, and he is also a distinguished member of the ONR research staff. So Juan, looking forward to your talk.
Yeah, distinguished. I was never distinguished before. I was like, extinguished? Yeah, there's no emeritus, they're extinguished. Well, thanks everybody. Thanks so much, Henk, for having me here. And I understand this is the time to go skiing and everything, so I'm sure you stayed here just for this talk. So what I'm gonna, old-fashioned pointer. I love this. Once I saw a talk by a colleague of mine, and he was looking for a pointer. He went out from this big hall. He went out, and then he came back with a bush. Alan Newell. Yeah. So anyway, so what I'm going to tell you about is about data assimilation, which is a sort of a now established technique, at least in climate and meteorology, for combining data and models and their errors. And I'm not going to assume that you know much about it, but if I assume way too little, then let me know and I'll hush it up a little bit. Okay, so basically we have for time-dependent problems, 3 estimation problems, and you're essentially given a random time series, usually very high dimensional, and the idea here, we call this retrodiction, is, for example, if you take this time series that comes from models, observations, controls, and what have you, and you might want to reconstruct the past, run an estimate of the past. Nudiction is actually the word for trying to construct the initial conditions at the current moment, so this would be something that the weather folks would be interested in doing, trying to get their models initialized properly. And then there's the prediction problem, and the peculiar thing about the prediction problem is that, of course, there's no observations being used. Now, we have a way to get around that, and part of the dynamic likelihood filter is a suggestion as to how to get around that problem. Okay, so now how do we combine these? The most popular way to do this is actually using Bayes, and essentially what you do is you have a prior and a likelihood, and you want to estimate x, which is your state variable, y are your observations, and the prior is usually informed by a model and its errors. And then the likelihood is usually informed by data, by observations. Essentially, that's how it's done. Now, we're told that lots and lots of data is good, and the more data, the better. And so here's a situation that you might have. You have a lot of data here, and you're told, okay, I need a model for that data. You kind of look at it and say, oh, it looks like it's a zero mean process, and maybe I'll put a Gaussian on this and just go home. The one thing you might never do is to say, well, maybe I should look at less data. That's something that your impulse would be not to do that, but if you had done that, then all of a sudden you said, oh my God, it really wasn't at all a Gaussian, this is actually some sort of a multimodal process, right? So the point of this is that now we're doing all this machine learning and so on and so forth, and more data is better and so on and so forth. But it's very easy to get fooled, and I think everybody in this room is a dynamicist in one form or another, and the idea is that models do have a very strong role to play, even in this machine learning world. So how did I produce that data? Well, I just simply did it with this little simple little stochastic differential equation, which essentially has a drift term here that that has two wells essentially with 3 stationary points, and one is unstable and 2 stable points, and we could call this the hot and the cold, if you will. And essentially you have particles getting kicked around between these two wells, and every once in a while they transition from one to the other well. Now, but if we were only doing data, if we were only doing modeling and we're doing estimation, and I asked you, well, if this is the cold weather and this is the hot weather, and I asked you, well, what's the mean weather? You're gonna say it's somewhere in between, and you're like, that's the most ridiculous and useless estimate I can think of, because either I feel very cold or very hot, but it doesn't seem to be right to be saying that we're in the mean, right? So the Bayesian estimate allows us to take into account some of the history. And so, for example, this is a manufactured data set from a hot to a cold system, and usually this data set has certain uncertainties, and we don't measure it everywhere or at all times. We measure it at certain times, let's say at unit times, and with certain uncertainties. And let's say we're going to use that data and that little stochastic model to make an estimate as to what's happening. And so again, we put it together Bayes formula here, and the way you play this fairly is you want to use your prior essentially to inform the likelihood. When you're cheating is when you use your prior to inform your posterior, and that happens. There's a lot of papers in which people are very pleased to see what the posterior looks like, and all they're doing is they're driving with a model the results that they like. So there is subtlety in using these things. Now, working with probabilities with state variables that have high dimensions is very hard, and so there's a big industry involved in how to find moments of this distribution. But if this problem is a linear and Gaussian problem, there are optimal methods called the Kalman filter, for example, or Kalman smoother, I should say, or the 4D bar, maybe you've heard of that, that actually give you the first two moments, which are the only moments that you'll see because it's a Gaussian linear process. But for high order, but for nonlinear and non-Gaussian problems, people like myself and many others, maybe Henk, you dipped into data assimilation at some point too, right? Yeah, everybody's tried their hand at this data assimilation game. And the key thing is to try to get this done in a non-Gaussian problem, but in high dimensions, it's a very hard thing to do. But we're making some progress. Okay, so this is a paper I quote all the time. It's by Bob Miller and Michael Gill. And I don't know this guy here. Anyway, these guys are fairly well known. Michael Gill is certainly known. And so what they're doing is they're looking at using data assimilation to do the problem that we just did. And essentially, this is a result that they get by, they just put a 10% uncertainty in the observations, and they run the model, and they basically use an extended Kalman filter, which is a linearized version of a least squares. And this is what they get, is the filtered solution is the mean, okay? And this is the estimated error covariance. Now, the filtered solution seems to know that something is happening. It does make the transition to the other well. But what's particularly problematic about this picture is actually not the mean, it's the covariance. It tells you that we have a lot of certainty in this, a lot of confidence in this estimate. And so that's the problem with these ad hoc methods or linearizations, is that even in this case, where the filter actually fails to make the transition, they just added more noise to the data. It doesn't make the transition, but it tells you that the estimate that they got is very, very good. Now, we use these methods actually to apply planes and do all sorts of things, and the way it's done is you take these linearized methods and you just drive it with lots of data. So essentially, if you have lots and lots of data and the data is very, very good, very certain, you can drive any dynamic problem into whatever it is that you want, and that's how an airplane will do it, or a sailboat, or whatever it is. The model is very crude, but essentially relies on a very, very good likelihood. Okay, so now what's the solution to this particular problem? There are methods for solving this estimation problem. You can solve for the full PDF. Here I started the PDF with a double well, but then this is the actual posterior estimate. And this was found by a method that long ago that we proposed. It's able, if you're busting at the seams, to calculate it on a computer, but it can't handle very high dimensional problems. But there is optimal solutions to this, and so that's what it looks like, if you're interested. Okay, now what I'm going to do is I'm going to tell you something about a problem we're interested in, which is making predictions. And there's a method for data assimilation that I suggested, which is called the path integral formulation. And so, and I love these cartoons. And so this is what a path integral is like. So in a path integral, it's just an integral of some function L, and you have here, L here is, well, it could be an action, or it could be a Hamiltonian or something like that. And what you're doing is essentially going in time from a birth to a death, and you take an infinite number of paths from one to the other, and then you use a least action principle to decide which one is the path. So apparently this path, the least action was public school, crappy job, marry, 21, children, divorce, retire, and poverty. But there are other possibilities, as you can see. Like this one, drop out of public school, join band, record deals, sex, drugs, rock and roll, money, sex, death. So essentially you take all possible paths, and then you apply the least action principle to choose one of the paths. So we're going to use it actually to do data assimilation. And so what we think of is in time as a chain of actors, and they're all linked with each other because, let's say, through a discretization of a model, let's say, okay? So time actually is just simply the index of this high-dimensional actor, and all of them are chained to each other. And then you essentially bump them all many, many times and produce all sorts of paths, and then you use the least action principle to come up with the path that this whole assembly of individuals take on. And so this is a caricature of what happens. The data actually winds up being like pinning potentials, okay? And of course there's uncertainty. If the uncertainty is greater, then the pinning potential is less strong. And when the uncertainty is small, then the pinning potential is stronger, and so there'll be a tug towards it. And as you can see, these things are sort of relaxing towards the mean of the model, which is 0. Okay? So I just want you to have this sort of caricature picture of what it would be like to do this problem in as a chain of actors, and they're trying to relax to some state. Okay, now, so what is it that I'm taking paths of? It's actually a distribution that looks like so. The posterior of the state, which is just the conjugate positions of these variables, given observations y of the pinning potential, is proportional to something that you can sample. And I don't want to get into the details as to how this is done, but basically the technique is you're sampling the full posterior distribution. That's essentially what it is, but it's interpreted as a path integral. Okay, so now let me get to the prediction problem. So the standard prediction problem might be something like this. You're given some data. Now this is getting really old. This is 380 ppm. This is very old. And so now what you want to do is you want to estimate what happened here. Of course, now we're over here. I better update this thing. Anyway, so you say, okay, fine, I'll try to keep you an estimate of what the CO2 might be at this point. And you might say that this is the estimate, and you might say it's this one or it's this one. So the point of this is that depending on your estimation technique, you can get different estimates, okay? And they're all going to be optimal. Well, They don't have to be optimal. But all these three estimates are actually optimal in some way, okay? So which one is the one? Which is the one that you're going to report from a physics point of view? So, so there's two problems here, right? The method matters, and also there's some difficulties in making predictions. Now, in the case of using the path integral, so this is sort of the least action principle path for this system of particles. And then you want to say, okay, this is the last observation was at present. What's going to happen next? Well, the only thing you can use is the model, right? And so the prediction is going to be something like this, because the model relaxes to a mean, which is 0. And you say, oh, is that really where I want to go? So the point is, well, how do we actually make use of something, or replace it for Bayes, or something, that allows us to actually look ahead in time? Okay, now why am I interested in these sort of things? So originally, I was going to work with Kerry Emanuel, we haven't gotten to it actually, at making better predictions of the eyes of a hurricane. And so this is a path of a particular hurricane, and making incremental better predictions in hurricanes is a big deal, because even if you increase your certainty by 15 minutes, you can measure it in billions of dollars, right? So it's a good place where small increments actually pay off really high. Now the idea here is to say to a company that sells plywood, I'll tell you where to put your trucks within an hour of where the storm is. Would you do that? And the answer to that hopefully is yes. And if they say yes, then it makes it possible for the people to self-rescue themselves and not get gouged on materials. So, okay, so we haven't gone to the hurricane, so I'm going to do a little more humble problem. This is back in Oregon State. They do a lot of wave stuff. And this is one of these wave tanks. And we're going to do an assimilation of observations from the wave tank, and maybe perhaps a model of these waves by some favorite shallow water model or something like that. So we're going to play this game. So it's a vignette. And so we're going to think here, X is here along this track, along this way. And we're going to put sensors here, here, here. So sensor here, sensor here, sensor here. And then we allow the wave to go through. Now this is a periodic wave tank, not like that one. But anyway, this is a periodic wave tank, so it goes like this. And what you're going to see is if these are going to inform the likelihood, we're not going to get all that much information, right? So you get this wave that just comes through and maybe hits one, maybe two of these guys. You don't get all that much information. Well, actually, information that there's no wave there is also important, but the idea is, well, maybe we can do better. And so the proposal for the dynamic likelihood filter is the following. These might be places where we're measuring, but this is a hyperbolic problem. It's a wave problem, and information travels at a finite rate. And there's not too many places where this information should go. It should go sort of along characteristics. So why don't we take the likelihood and dynamically move it forward? Why not? So instead of measuring these just 3 spots, then we take data that have happened before and we project it forward in time, and so now we have this many spots. And we project it forward and so on and so forth. Of course, theorem of no free lunch, we get uncertainties that grow. So the data that was here is not very useful here, but it's still, why not account for it? Now, why is this a good idea? Well, in waves, the one thing that you want to do is you want to get the phase right? So that's one of the most important things out of a method, and people don't pay attention to phases when they're working with Kalman filters and so on and so forth. So, okay, so this is a proposal for a dynamic likelihood filter. The toy problem might be that something like this, a one-way wave problem, and I'm going to have uncertainties in the speed, perhaps in the forcing, but I'm really more interested in the speed. So you think of the forcing as being some mean value and some known noise, and the same with the speed, some mean speed and some known noise. And there's a corresponding problem along characteristics, which means if I wanted to solve for this problem, I could solve it along characteristics, the wave characteristics. And if I do that, this is the problem that I would solve. And as you can see, there's uncertainties in the position here, and the uncertainties in the forcing will show up over here, okay? All right, so far I haven't done anything that is not textbook. But I'm going to actually move the data around. Okay, so the model is still going to be informed by some, the model is still going to inform the prior, just like before, and the observations are still going to inform the likelihood, like before. However, we're going to propagate the data along characteristics and take into account that as it's propagating through the characteristics, they're actually inheriting uncertainties. All right. So the picture is again this sort of thing. Now, what is this thing here? This picture is a picture of a noisy wave. And this is in fact a case in which I can actually solve it by hand. So this solution is the true solution. And the proposal is something like this, is that this is just equations for the observations at some later time. Something's cut off here. It says that the observations, this observation projected onto the next one more or less looks like the old one, plus some uncertainty. And this A matrix is the one associated with uncertainties in the position. Okay, so it inherits uncertainties due to that. Okay, so now you can play you can really scrounge for data in the following sense. And so this is a proposal. So let's say this is along the tank. So there's 11 stages along the tank that you might want to have data. And in, let's see, how do I do this thing? So what I'm doing here is I'm showing you the uncertainty of observations at some given time, and you sort of catalog them, you put them, the observations, and you put them in different ranks. It just means that these are more uncertain than these. And then you map onto, from Lagrangian to Eulerian frames, these uncertainties. And so, for example, at station 9, I can go back in time, or in uncertainty, to this one. It's very uncertain, but I can actually inform what happens at that point. Because there's some data that at some point or another, long ago, had propagated to that point. And then this one is going to inform 5, and this one, and so on and so forth, right? So you can play this game in some way or another. Now, and you can inform the whole tank if you wanted, or if you could. Oh, the other thing I can do is the following. So, actually I can do it here. I can do the following. So, not only can I actually update it to different times, but I can actually do it in between observations. So not only am I getting likelihoods at places where I had no business looking for a likelihood by just projecting it in, right? And so basically what I'm saying with that is that I'm keeping the phase very, very accurately that way, right? Because I'm actually assimilating along the phase rather than space and time. And then, and then the last point is I can always say, well, this is the last observation I had. Why don't I just project forward the observations, and then I can actually do a Bayesian statement forward in time. Now, it could be controversial, but it's probably still useful, right? So this is one data assimilation method where you can do Bayesian assimilation in the future. Okay, now, what's the mechanics of the calculation? For this particular problem that I just presented to you, this one-way wave problem, it's a linear problem. And we can use an optimal method that already exists called common filter. It gives you the solution. So there's no need for anything fancy for this particular problem. But, so here what I'm trying to say is, there's the method of finding the estimate, and there is the dynamic likelihood filter. So the dynamic likelihood filter says, if you have a hyperbolic problem, this is a recipe for actually producing a different likelihood, and then you take your own estimation method and apply it. So you can do common filter, extend ensemble common filter, whatever it is. Here we're using common filter because it's a linear problem. Okay, so in terms of the common filter, what you're going to have is the following. The old way, so you would have, let's say, data and observation, this is the model state, and these are observations, are related to each other perhaps through some projection matrix and some known noise. For the dynamic likelihood filter, you have now many real observations plus projected observations, and so you're going to take those into account. And you have a way to update the estimated covariance due to projected forward observations. There is a recipe, and the recipe is pretty simple. Okay, so the way this would work in common is you still have common is essentially a forecast and then an analysis. Okay, so the forecast says if you have a model, linear model, the best estimate as to what's happening in the future is to take the mean, which is you zero out the noise because the noise is zero mean, and you just move forward. That's the best estimate of what the model says. And then you take into account observations and models through an equation that looks like so. And so this might be your forecast. And then there is something called the analysis stage, which now looks at the data and actually combines like so in to make the estimate of the new place. This is now the posterior mean, for example, of this thing. And where that comes from, the simple thing to do is you form the posterior covariance. You just write that down, and then you say, well, the common filter is going to be the minimizer of the trace of the posterior covariance. So you write down the trace of the posterior covariance. And a little homework problem that I give to my students is find the minimizer for the trace of the covariance. And if you do that, you're going to get something called a common gain. This K comes out of minimizing this trace. It's just a little calculation. It also tells you how to update the covariance, the posterior covariance. Okay, so that's the Kalman filter. So in the dynamic likelihood filter, you do the forecast just like in the old way, so you update you create predictors for the estimated mean in the covariance. And then there is the analysis stage, but now it's a little more complicated because not only are you doing it on data that you're observing at the moment, but also stuff that happened before. Okay, so it's just, otherwise it's not any different. Okay, now, so here's the sales job. You pick the best picture that you can do that generates a sale. And so the way we're going to play the assimilation game is as follows. This is going to show you how good the method is, at least by the eyeball metric. And so what we're going to do is we're going to do waves, and I'm going to use for a model a Lax-Friedrichs realization of this thing. Now, why Lax-Friedrichs? That's the model they gave you. It's not the best way to solve a wave model. This is what they gave you. The model is intrinsically whatever it is that they give you or that you choose, right? So you could have chosen a better hyperbolic solver. They didn't give you that. They gave you this kind of model. So this is the Lax-Friedrichs, and it's highly dissipative. And so this is the wave it produces. The CFL is very low, and I purposely put it low just to make the model look terrible. Okay, so there it is. Okay. Now the model doesn't have much in the way of noise, so there it is. Now for this particular problem, I was able to solve by hand. So this is the exact. This is one realization of that one-way waves, right? Every time you write down a solution, it's going to be a different one, right? So this is a realization, and we call that the exact one. Now the common, this would be the optimal estimator. If you didn't know anything about the dynamic likelihood filter, it would be something like this. And you can see that the common, so the model, of course, is terrible, right? So it's producing a lot of uncertainties. The data, on the other hand, is really good. And so what's happening is the data is being measured every, as you can see, every place here. And it's highly correcting all the indignities that the model is putting into the estimate, right? So it's a pretty severe situation, but this would be, if you didn't know anything about the dynamic likelihood filter, this would be your optimal estimate for this particular problem. And this is what you get from the dynamic likelihood filter. So you still see some remnants of these corrections, right? So you are corrections and everything, but by the eyeball metric, I mean, they're not too bad, especially the phase is actually quite good. So, and I'm exaggerating the fact that I picked a very severe case to compare. This is a method that actually does a really darn good job. And like I said, you can actually, this is not a case where I show this, but you can actually make forecasts of the future. And they can still, they still need interpretation, like any estimate does, but it's an interpretable estimate, and you can actually say how to interpret it, because it's an estimator that minimizes the trace of the covariance, for example. Okay, so this is another picture that shows you how good this particular problem does. So this is the variance norm, and the DLF is the blue, and the Kalman filter is the red. And not surprisingly, every time they make very good measure, this is a case in which the measurements have very small uncertainty, the model has very high uncertainty. So at the times of measurements, of course, the covariance, the trace of the covariance gets pulled down, but otherwise then it starts growing because of the model. Whereas the DLF actually keeps nice and steady. Now, if you're asking, well, wait a second, the Kalman filter should be optimal, so how is this beating the optimal? The reason is because we're actually using, effectively, a different posterior. I mean, so the posterior in the Kalman was just simply observations, and the likelihood informed by observations, the model by prior. In the dynamic likelihood, it's model for the prior, but the likelihood is many, many new terms in it, right? So it's not the same distribution, okay? So that's why this could be even better than that, even better than the optimal, because it's a totally different thing. Does that make sense? Okay. Now, as I said, one of the key features of this method is that it does a very good job at getting a phase, and one way you can sort of estimate how well it does with the phase is you can compute the center of mass of this wave, a lumpy looking wave here. And so if you do that, you'll find that the exact one is the black one. That's sort of the center of mass of the wave in time. And the blue is the dynamic likelihood filter, and that does better than everything else. Okay, so it does a very good job at tracking phase, which is good. Okay, so the DLF method, so it only applies to hyperbolic problems. We're now trying it on strongly advective flow, so advection diffusion, but where the advection is very, very high, and so we're producing a split-step version of this method. Like I said, it could be incorporated into any Bayesian assimilation scheme you want. And where it works best is when the data has low uncertainty and is sparse. That's what this thing is designed to do. When the data is got high uncertainty, then it works no better than anything else. So at least if you're, under other circumstances, you get the same answer as Kalman. It's only in this case where it really beats it, because we're taking very sparse data at a very high certainty, and we're exploiting it very judiciously. And so you get sharper posteriors sharp posterior uncertainties, and the key thing here is that we're making use of the data between observation times, and also we can go into the future, so we can actually make Bayesian future predictions, at least of wave problems. Okay, so I'm going to switch topics, but before I do that, any questions on sort of the idea here? So, yes?
Can I ask something? So, you're using a model, and in the example that you gave, the model was bad, but I can think of an even worse model. So, are there any conditions on the model that you need to have?
No, so what we're doing here, this is the key thing. When you're reading a data assimilation paper, they're really making a mistake by not telling you exactly what they're assimilating. So the game I'm playing is the following, and this is irrespective of using DLF. This is just data assimilation in general. For me, the model is not the best thing that captures the dynamics that I'm looking at, it's whatever I'm given. For example, it could be a computer code that has whatever it is. That's the model, and for that model, I have that model and I have its uncertainties. I need to know those two things. And for the likelihood, the same. I'm given some data, it has to be zero mean noise, so you have to unbias or whatever it is, but it is what it is, right? So now, if you use those two, you make an estimate. And so the estimate has to be interpreted in terms of what it is that you put into it, right? So I have to say, well, this is the posterior of the wave velocity, given observations, for a model that was a Lax-Friedrichs model with this uncertainty, and for data that had this uncertainty. So the thing that's bad in data assimilation papers is they never tell you exactly what it is that they're doing. So every time you get an estimate, and especially when they're comparing things, you have to be careful what they mean. Now, if I use a better model for or even if I crank the parameters for the Lax-Friedrichs to make it a better looking thing, I'm gonna get better results because the model is gonna do better work, right? It's not gonna work against the data. So now I forgot if I even answered the question, but basically what I'm getting at is, this is independent from the estimation technique, right? But how you actually interpret your estimate has to do with what it is that you put into it, right?
Yeah.
And that's something that people fail to do, is to tell you what it is that they did in the first place.
Yeah, but I can imagine your model will also just fail if your methods would fail if your model is completely rubbish.
Yeah. Now, so what I tell my students is, the good news is you get an answer, the bad news is you get an answer. So you have to say, now that's becoming more common now, and even there's an apology for saying that you can get an answer and be left with it, like in machine learning, it's done all the time, right? I just cured dandruff, you see it, done, right? So, but what's happening in machine learning, actually, people are learning about estimation methods. Bayesian learning and machine learning methods are crashing at the moment, which is good. And essentially now everybody's looking for interpretable machine learning techniques. And what this is this issue of interpretation, right? What does this thing mean? Is it optimal in one way or the other, whatever it is? So this is a big thing. And it's a good place to work in if you have some ideas. And the way to do it, for example, in a dynamics place is you make it interpretable in terms of dynamics, for example, right? Other questions?
Is this used in particle filters also?
Yeah, so we're...
Because it seems you improve your likelihood, right?
Yeah, and it's a natural in particle filters, in fact. So Peter Van Duyn and I are working on a particle flow filter for highly non-Gaussian problems, and we're going to be doing these kinds of things on it, and it's giving very good results. We're actually combining with machine learning because you have to. No, because it also is a natural place in which you can talk about surrogates in an interpretable way. Okay, so let me tell you about, I'm full of problems. Here's another problem. It's called the trend problem. And the trend problem is something like this. This came because a student came into my office and said, can you tell me how it is that I can estimate whether it's gotten warmer or not? And I'm like, what do you mean? Well, I want to, measure it, and and I'm like, that actually is very difficult to do. I have no idea how to do that. How can you tell whether it's getting warmer, right? Just by, individual. And instead, of course, I said, well, you take these climate models and you run them, and there should be a way to get that. But when you do it from data, it's a very confusing thing to do. Okay, so this is called the trend problem, and what you want to do is you want to have an executive summary of a signal. And actually, in economics, people do this. There is such a thing. I forgot the name of the filter. It's essentially a glorified high-pass filter. It takes out most of the noise, and it just basically leaves out the trends. And the trends is in what you think it is. But for us, this is our signals, right? This is what a signal for us looks like. And we say, okay, so now we have to calculate the trend for this thing. You say, well, I don't know. But, you say, well, okay, I can see there's some some structure here, then maybe I'm gonna do something windowed or something like that to report it. And so how do you do this in sort of an automatic way? So problems that are multi-scale in spectrum with big globs in their spectrum, how do you actually calculate a trend for that, is the question. And the answer for us is called a tendency. Okay, so what is a tendency? So we take a signal and we want to produce an executive summary, and the histogram of that executive summary, which is called T, will be such that it should be more or less the histogram of the residual, the difference between the signal and the tendency should be nearly symmetric in some way, or at the very least that the variance has to be smaller than the variance of your original signal. And it should have low complexity, but not so low that you lose everything, right? Okay, so let's try to put something like that together. And one way to do that is through something called the intrinsic time decomposition. I bumped into this by accident, and this is a time series analysis scheme that is purely algorithmic. They use it all the time, and they don't understand what the hell this thing does. And this is how it goes. Actually, the empirical mode decomposition is another one like this. In fact, it's sort of related to this. So 2 things I'm going to tell you very quickly is what it is that this thing does, and 2, a suggestion as to how we actually would calculate a tendency. Okay, so the decomposition is something, this is like a constant, and these are rotations, B is baselines, and it kind of looks like a Fourier series. Now the rotations are such that the baselines are going to go below every maxima and above every minima. You weave it through, okay? We're going to show you in a second. And every baseline can be written in terms of the baseline of the next stage plus the rotation. So going up in R and B, in J, sorry, makes them smoother and smoother. The least smoothest is the 0th, okay? So here's the procedure. You pick out the extremas. Oh, let's use a fancy pointer. So, you know, this extrema there, there. And then you put in this blue line here. It's a simple looking, basically it's a linear interpolation. And then you subtract the baseline from the data, which is the black, and then you get the red, and that's the rotation. And you rinse and repeat. You do this over and over and over and over. Okay, so that's how it's done. Now, we're like, okay, what the heck is this thing? And so we spent some time actually trying to analyze what this thing does. What does it mean? And it turns out it's a diffusion map. Now, one thing that happens is if you put, for example, let's say extremas at every single point, random, but otherwise they're all extremas, at every point between 0 and 2, 5, 12, and you do this decomposition, the distance between the extremas fades off very quickly. J is, of course, the level, so in 6 levels, it just clears out everything. It's really fast in clearing out things. It's highly adaptive. And we fussed and fussed till we finally figured out what this thing does. And we found that if we choose the right tank coordinates, and I'm not going to write down the expression, we can actually put this into something that looks like the spectrum of this discrete matrix actually winds up being universal, winds up being cosines. So this thing actually is a diffusion mapping. We could even calculate its eigenvectors and eigenvalues. So what this decomposition does is it actually mimics this advection diffusion equation. That's what it does. T actually is the level, J1, whatever it is, and X is sort of a strange measure of time, okay? Now, here's the interesting thing. This is why I got interested in this particular scheme, is that the scheme actually, let's go back to the signal. So, you know, you look at the signal, there's 2 things that are interesting about the signal, especially if you're a dynamicist. One is, of course, in this direction, right, you can write down a PDF for everything that happens with the temperature, right? But this axis also has statistical information that we often don't use, which is the position of the extremas, right? You know, in dynamics, if we see something happening, we say there's got to be an explanation for it. But maybe there's things that happen that don't need an explanation, and that's the whole point. So the decomposition makes use of this, as well as this statistics, okay? That's what's interesting about it. So the idea is, This is, oh well, anyway, I'm gonna skip this thing, which is the general abstract nonsense as to how we figured out what this thing was. I'm gonna skip that and instead just go directly to finding the tendency of the signal. So we're gonna do a decomposition, I'm gonna show it to you in a second, and we're gonna pick one of the baselines to be the executive summary. So here's our original signal, and here's the full decomposition. This is the I-score data. It looks a little strange because it's been stretched out. This is baseline 1 plus rotation 1 is equal to this. Baseline 1 could be written in terms of baseline 2 and rotation this, and so on and so forth. So this is a lossy decomposition. And then by the eyeball metric, you say, okay, I want to take one of these baselines that's, you see it's losing complexity. And you kind of have to look for the Goldilocks, right? And so the Goldilocks looks like it's a maybe 2 or 3, maybe 4 is already too terrible, but maybe 3 is a good one, okay? So how do you get something that picks out that between a 2 or a 3? So now you think of the rotations and the baselines as two trains passing in the night, and if they pass just at the right time, and they're sharing information on each other, there's a point at which they're sharing just about equal amounts of information between them. Now we measure that using something called Hellinger distance, but basically when the Hellinger distance all of a sudden takes a little break, that's where we say we pick our baseline, and it picks out B3. I hope that's right. You won't know it. Okay, let's say it's B3, I hope that's right. And that's how it's done. So we use basically a information theoretic construct to pick out which baseline is going to be the tendency. Okay, so this is what I just said, and I'll just show you now what that tendency looks like. So, and green is the original I-score data. Now, by the way, this I-score, this is the Vostok I-score data, and this is, it's actually printed backwards. This is present and that's the past. And in the present, there's more data than in the past. That's another thing, that's a feature of this data. And in red is our tendency. And some of you are going to say, well, that looks right, and some of you are going to say, no, that looks really strange. Now, what it's doing, right, so there's a lot more data here, as in more time stamps, and there are a lot less here. So the tendency is latching onto that notion because there's a lot more extremas in this place than there are here. So it'll do what you tell it to do. There's nothing fancy about this. Now, if I take my signal and subtract from it the tendency, if I compute the histogram of a green signal, it looks like so, right? So highly non-Gaussian. If I take my tendency, subtract it from the signal, then I get this red thing that looks very lumpy looking. And I can say, well, you know, I can certainly parameterize this very simply using some stochastic model or statistical model for this distribution. So therefore I can sort of get a surrogate model for the I-score that is just this red thing, the tendency, plus this simple parameterization. And so that's how we're going to use it. So the idea, I'll skip this. Oh, here's another signal. This is Tom Howell's famous hyper multi-scale signal. This is a monstrosity that looks like so, and this is the tendency, and the green signal is that monstrosity. And again, it pulls out something that looks very lumpy. And so it's doing what we want it to do. And so, just to conclude then, what we're going to try to do is the following. All these estimation methods that I talked about, common filters, path integrals, all this stuff, works on what is called aleatoric models, aleatoric noise on models and data, right? So it's this term here. For convenience, it's zero mean, but basically you need to know what this term here, the noise model, is for this dynamic of X. But it does not know anything about epistemic model. Epistemic model error is just errors in unknown physics, parameterizations that you have to put in there. And unfortunately, the statisticians don't know much about dynamics. They like to study the epistemic error. For us, if we really understood the epistemic error, we fix the damn model. I mean, why carry it around, right? Just fix the darn thing. So the idea here is that you're looking at some parameterization you don't quite understand, which is called U, And you can think of it also as a control parameter, and you can use machine learning techniques for that, but then you have a very ugly looking system to solve, which is the Jacobi-Hamilton-Bellman problem. In infinite dimension space, that's a mess. So the idea is to say, the hell with that. We're gonna use this tendency to actually look at models with known physics, so without a U and those with a U, and essentially try to optimize the U using the tendency for the surrogate estimation problem, and that we can do, okay? So it's a quick and dirty way to include unknown physics in some interpretable way, as well as the estimation of the editoric noise. And the only change you have to make then, the big change, is that your posterior now has to look a little different. It's got more terms in it, because you have to have U, which is this unknown physics, or the control parameter, if you will, but for us it's just unknown physics, that you also have to sweep through. But that's easy to do because we have nice surrogates for T, okay? And so that's what we're gonna do next. And with that, I end. Thanks.
Good. Any questions from the audience? If not, I'll start.
Yeah, of course.
So what does this tendency mean? I mean, you have the Pleistocene ice age signal, right, from the Rockford ice core.
Yeah.
What does it mean? Can you deduce that, or is there any? And is it the eccentricity induced signal, or I mean that probably is not because it's too big, but
That's
is
right.
it related to that, or
No, so okay.
can you trace it back in some way, right?
Yeah, so you're right, you want something that interprets this thing.
Yeah.
Now, the interpretation that you can use on this is the same as if you say, okay, Fourier is a L2 optimal estimator for L2 periodic function, this or that. What the tendency is the best, well, maybe not better, it's an estimator of the Kullback-Leibler distance between the baselines and the rotations, okay? But in another way to look at it is the following, is that in terms of resolvable extremas, okay, the dynamics that you can resolve on this one has extremas of a certain size and everything's smaller than that, sorry. I was gonna go this way, it's smaller. And so, because it's a diffusion map, right, it's just killing off adaptively scales that you are not gonna see. So that's the interpretation. It's still abstract, but at least it's interpretable. It's not just simply some. Now, does that mean something in terms of physics? I don't know, right? But you, yeah, so you can't make an interpretation physically. The way you would include physics is the following. You're given an executive summary, you say, okay, this is a process I need to understand. I have some dynamics and I'm gonna see if I can explain this, and then this, and then this, and you keep knocking off things, right? And then at a certain point, you say, well, the rest is just noise. So that's how you would use this thing, right? Or that's how you would use it, say in the stock market. Well, I can understand this and this and this part and this, right? So that's how you would use it. And what we're gonna do is turn it around, right? And so what we're gonna do is we're gonna throw in a U term and make it do something that it will actually mimic the I-score data, and then pull it back as much as possible, and then say, okay, this is the minimal amount of new information you have to put into this model. It will tell you what it is, but it'll tell you how much is, so it'll track nicely, and everything else is tracked by a noise term. So it's still, I think, useful. This is not an orthogonal decomposition, which is also makes things hard to interpret, right? Because you got things that are very wiggly here and not so wiggly, and you're saying, oh, that really makes that's a real, no pun intended, buzz killer, right? Because it's like, we're used to thinking in terms of Fourier wavelets and everything is in nested subspaces. And this doesn't allow you to do that, but it does allow you to do it in terms, if you take the stuff and you map it, if you take the extremas and put them equally spaced, it looks very uninteresting. And so that's the key thing, is that the extremas make a difference. And that's what makes a difference in dynamics. Yeah. Yes.
So if you have data survives a certain trend, so it's quite smooth, and then does a rare excursion and goes back to having a trend and keeps doing that, what do you get out of this?
Let me see if I can find, let me see if I can do this on the fly. I have one example. I'm gonna do it the high-tech way, since we're doing it. Okay, so I have I can show you afterwards the actual signal. So I had something that looked like this, and then I stopped, and then I had this. Okay, and what, oh God, now I don't even remember what it gave me. So what it did is it gave me this, I think. Something that looks like that. Now, if I had something, I remember something else. I had rain in Tucson, Arizona. It's a very dry place. It's either raining a lot now. So it looks something like this. And the tendency was this, something that looked like, I don't remember it long. So there was about as many extremas on the top as extremas on the bottom, that kind of a thing. On the other hand, if I had something monsoonal, right, so I had lots of extremas here, then it started following this, and then going back like that. So it's very sensitive to, well, what I think is dynamical problems, if the data comes from a physics problem. I can show you. Usually I had a card trick, which was give me a data set and we'll try it on the fly, and I would do the analysis. I could do that now, but I'm not gonna try. Curiously enough, we tried data from Froude, his experiments on a pipe, turbulence experiments, and I got these structures in it and during a talk, and I'm like, what the hell is going on? Something very wrong. I think what happens is when they transcribe the data onto the paper, you know, they did it by pen or whatever it is, someone's fudged the data a little bit. And you can see the fudges, because there's structure in there that should not belong in there. And it picked it out, so it was interesting. But I think it's because, I don't know how they would transcribe it into a paper back in the 1800s or whatever, 1890s. But there is the element of human fixing it. Anyway.
Okay. Any more questions? Come on. Yeah,
But so, for example, in this example you showed, it depends a lot on the extrema. So if you had, like in Dijkstra data, more data in a region, then you necessarily have more extrema. Is this a good thing or a bad thing for the model?
Well, no, so that's where the interpretation comes in, right? So what is the way to sort of turn this around is the following. From an empirical standpoint, if there's more data, you should pay more attention to it. And this thing is making you pay more attention to it and saying, it's screaming at you and saying, okay, look, it's here and it's doing a lot of stuff here, and here it's not. And if you have trouble interpreting, it's your fault, right? Right? So I think I rather that than the alternative situation, which is all of a sudden it gives me something that says, well, I'm gonna cook up what's happening between here and here. Even though there's lots going on here, I'm gonna cook up something and not tell you anything at all, and then do, So it forces you to think, when I present this to a statistician, this makes no sense whatsoever. They say this is crazy. But if I present it to people who are used to doing dynamics and are used to looking at a signal and trying to interpret why it is doing these things, it makes some more sense. Now, in machine learning now, I can say anything, I can get away with it. This is a machine learning technique, right? It's a time series machine learning technique for producing surrogates. Yeah, so, but it has a little more interpretation. The interpretation has to do with the amount of extremas that you allow this filter to pass. That's the one you pick. And it says, look, I won't tell you anything about extremas or curvature or whatever it is in this strange coordinate set. I filter everything from there on. And I just present it as just the Gaussian process or something that looks very simple.